I'd like to thank the organizers, and particularly the coordinators, Azana, we heard, Srini, and Bill Goddard, for inviting me today. We all got, as speakers, a notice that said one of the most important things about the interface is the nonlinear dynamics. As Azana just described that, and the approach to equilibrium. So what I'm going to talk about today is a very important study that was started in Los Alamos in the 1950s, where people tried to find an approach to equilibrium in a simple classical system, and they didn't find equilibrium. They found a lot of other things that led to the development of nonlinear science, which is not my topic today, but the fact is it was extremely important, and there's still unresolved questions regarding how we approach equilibrium, and that's this metastable state. So here's an outline of what I hope to finish in my 20 plus, whatever, but I have a few extra minutes now. I'll recall the original Fermi-Pasta-Ulam-Tsingou simulation, where they talked about two different models, which we'll discuss in detail, and they found recurrences and superrecurrences. I will talk about the proximity of this alpha model to integral systems, and the alpha model actually was shown to be related to a continuum equation, the Korteweg-de Vries equation, and that was worked by Kruskal and Zabuski, and also the total lattice in the discrete version is closely related to the alpha model. We'll talk about that. I'll talk about the use of spectral entropy to quantify how far you are from an integral model. I'll talk about the existence of the long metastable state. I will explain the eventual decay of the deviation of the alpha model from the integrable system, the total lattice. And we'll start with how it eventually does approach equilibrium. And we'll talk about how the metastable state appears sometimes to be trapped in a sticky region of this very high dimensional phase space. Somehow there's a sticky region where it gets trapped for a long time, and conceivably a very long time. And I talked about mostly the alpha FPUT. We'll talk a little bit about the beta model. I'll describe these in detail, and then I'll give you the conclusion, the speculative relations on what will happen actually in the true thermodynamic limit, where the energy density is finite, but the number of particles goes to infinity. So this is a very important topic. So this is a picture of the three gentlemen you all know, Fermi, Pasta, and Ulam, from your left and right. And they set out to answer in 1953 the fundamental question of how equal partition and thermalization lead to occur in simple nonlinear dynamical systems. It turns out that those gentlemen in those days were not particularly great at coding. Fermi could code, but Pasta, who was later a computer scientist, and Ulam certainly couldn't code. So the work was done by Mary Tsingou. She's shown this picture here. I refer you to this very nice article by my colleague Thierry Dauchois in Physics Today, where he described her role. Mary is still alive, and so that's a fantastic memory. Let me recall the original results. So during the summers of 1953 and 54, these three gentlemen, and with Mary, used the world's most powerful computer, the so-called Maniac 1, to study. This was a joke made by Nick Metropolis, mathematical analyzer, numerical integrator, and computer. They made jokes of the names of computers in those days, and Nick Metropolis named it. So they tried to study the following big question. In StatMech, in an equilibrium state, the energy should be divided equally among the individual components of the system, and that's the equal partition of energy. How does this come about from reversible microscopic equations of motion? How does it happen? And to answer this, they studied the simplest model they could think of a classical one-dimensional solid, a chain of equal mass particles coupled by nonlinear springs. And of course, they knew that linear springs could not produce equal partition because you just use Fourier modes, and the Fourier modes remain constant. So this is a picture of the Fermi-Pasta-Ulam problem. We have n particles here. Typically, they took fixed boundary conditions, although I will be talking about both fixed and periodic boundary conditions. Potentials between the masses, the springs, had the usual Hooke's law term that leads to a linear equation of motion, and it had nonlinear terms as well. And those typically they studied systems of 32 and 64 sites. And they studied, this is the alpha model, this is the beta model. And this is a quote from Pasta-Ulam that this work was never published because Fermi died before it could be published, and so it was only published in his collected works much later by the University of Chicago. And Stan made this great quote. I'll let you read it. Fermi was surprised by this, and he thought that universality in mixing may not always be justified. He called it a little discovery. I should have put that in quotes, because it was far more than a little discovery. It led to a huge field of nonlinear science. So here are pictures of some results. You see the equations of motion in coordinate space for the alpha model, Newton's equations. Here are the equations of motions in mode space, in Fourier mode space, where you see the coupling of the different Fourier modes given by this term. And these pictures down below show that what happens in a simulation, this is our result simulating the Fermi-Pasta-Ulam equations. You see that, you notice that only in mode space, only a few modes are excited. And these modes really are very, very small. And if you look in coordinate space, you don't see very much. You see the thing going back and forth if you look at the coordinate itself. But basically, this localization in a few normal modes could lead to something which you might call a Q-breather, something which is periodic, but with a small number of modes involved only. So here's again, more results on the alpha model. Only the first few normal modes are excited. These are directly from the original preprint, taken out of the book. You can hardly read this, but the first only modes 1 to 5 are excited. This is at one particular value of alpha. Here we have alpha equals 1/4. I won't read n equals 32, and the time step was given by 1/8. Here is the same thing with a larger value of alpha. You would think the higher nonlinearity would lead to a more rapid recurrence, but in fact, the stronger nonlinearity leads to a shorter recurrence time. How do you see that? Here's the number of cycles. This first recurrence, almost 100% back in the initial mode. By the way, these are the 5 modes. You see them 1, 2, 3, 4, and 5. And you see 1 starts, comes down, 2 comes up, goes up, 3, 4, 2 comes up most in the middle, and this is about 97%. If you go to stronger value of the coupling, nonlinear coupling, you get a quicker return. This is at roughly 14,000 cycles. This is at 28,000 cycles. So that also has to be explained. I won't go into detail, but you can explain that. If you go still longer times, much longer times, instead of having the thing go to equilibrium, here's the first FPU recurrence, second, third, and it goes down, and then it comes back to a super period. And this is in oscillations of fundamental frequency. So you see, this is from the actual paper I'll show in a minute. So the super period, the super recurrences were discovered by no sign of equilibrium, even on these long time scales. In fact, instead of the solitons producing the recurrence, you have these super recurrences. And you see this paper from Tuck and Menzel, this picture and this picture. This is married Tsingou Menzel. So this is after she married Menzel. So let's talk about the relationship of the Fermi-Pasta-Ulam problem, the alpha problem, to the Korteweg-de-Vries equation, which is a continuum equation, a partial differential equation. So Kruskal and Zabusky use multiple scale expansion, which is familiar to all the applied mathematicians for sure, to write the coordinate in terms of a co-moving coordinate and a second time for small values of epsilon, plus explicit terms of order epsilon, and this is in their Kruskal and Zabusky's famous paper. And they discovered that if you want to have consistency in the multiple scale expansion, so you didn't have secular terms, you had to have the derivative with respect to the co-moving variable, that's u, it had to satisfy a Korteweg-de-Vries equation. So the point is, the derivative with respect here is actually the momentum. So that's what you see the recurrences in, the solitons is in the momentum. So that's an important point to remember. Here's the Korteweg-de-Vries equation, nonlinear term, dispersive term, and of course they balance exactly to lead to the soliton solution, which is given by this way. You notice that here the amplitude of the soliton is directly proportional to the velocity, and its width is inversely proportional to the square root of velocity. So the amplitude, shape, and velocity are totally interdependent, and that's characteristic of solitons. And they also but they also retain their identities in interactions. And that led to a whole field, as we know. So let's see what happens. You can watch how these things emerge from the initial state in the Fermi-Pasta-Ulam-Tsingou problem, the alpha problem. Now you'll notice I'm plotting the momentum. Here are the lattice sites. We did the simulation on 63-site system. And you'll watch as it develops in time. You see the value of momentum there, moves across. You start seeing these ripples coming in. These are the solitons. We'll run this up to about 400 time steps. And you see these individual solitons emerge. The fastest soliton there, the one's falling back, and we come to roughly, I guess I got to go 500. That's right. And you can see the string of solitons. It turns out, we'll show in a minute, there are 8 solitons that emerge from this particular initial condition, as was found by Koskela and Zabuski. So to see it better, we look at a still, which is a repeat of our simulation, and we plot at different instants of time. The blue curve is the initial state that they took. This is now X is the continuum between 0 and 2, excuse me. That's at time 0. At time t equals 0.32, we have the orange curve. And what you see here is starting to be a break. The nonlinear term is leading this wave to try to break. But in fact, instead of breaking, it gets smoothed out by the dispersive term. And at much later time, you see the 8 solitons quite clearly right there. Here's another example. This is actually now the coordinate itself and versus time going this way. And you see here the individual solitons are color-coded, the fastest and brightest being the largest. And you observe 8 solitons, which you can see by this virtual line. I won't bore you by counting through, but you can go through and see they cross. And when they interact, as we see here, you can just barely see it. There's a phase shift. That's the only effect of this interaction in these nonlinear waves. Very surprising when it was discovered, and therefore the name of soliton that Koskela and Zabuski gave it. What about the total lattice? There's the alpha FPUT problem. This is the form of the potential. And the total potential is given by this. It's exponential, subtracting these terms. And if you set V0 equals the lambda to the minus 2 and lambda equals 2 alpha, we see that the total lattice is the same as the FPUT lattice up to order to the 4th. So the total lattice, the FPUT initial state would be expected to co-evolve with the total lattice state before finally breaking away and revealing its non-integral nature. So how do we quantify this? First, you have to verify that the solitons that arise from the initial state in the FPUT are same as those that arrive in the total lattice. And second, for a more quantitative comparison, we need to look at the spectral entropy, which I'll soon define. So here's the emergence of solitons from the initial FPUT state. What you see here on the left panel starts out as a traveling wave moving to the right. That's really annoying. Okay, and basically what you see is these are the solitons moving up. What you can find is the time scales at which they break is exactly scaled by the FPUT time. It's correct. Here's epsilon. In the right panel, here you can see 8 solitons labeled 1, 2, 3, 4, 5, 6, 7, 8. And the 8 solitons are the fastest one. They're clearly visible at later times. This is the lattice site. Here's time. And those are the solitons. So here are the Q breathers. These are these exact time-dependent states that occur in the FPUT system. And for the parameters shown, this solution continues periodically forever, and therefore and similar in shape to the pairs of solitons found in the total lattice with periodic boundary conditions. So this continues forever. So it's a stable state that continues, is out of equilibrium and stays forever. Okay, thank you. So this is a comparison of the Q breathers to the solitons, and you see two here. This is for alpha equals 0.5 roughly, and the two breather solution will continue periodically forever. Oops, let's move on back. And so this is a comparison with the conoidal wave pattern found by Shastri and Young in the total lattice with periodic boundary conditions, and has similar structure to the solitons we saw. So they identically correspond to each other. Spectral entropy, I have only 5 minutes left. I will quickly define it. Basically, here, put the whole thing up at once. What you define is the amount of entropy in each normal mode, and it's in relative ratio to the total. And the spectral entropy is given by this. The scaled entropy is given by this. It's between 0 and 1. If the energy is all in one mode and stays there, then eta is equal to 1. If its system is equilibrium, you can show this by assuming by equilibrium you mean a Gibbs distribution. You can show that the average value of eta is given by this, so it depends on the size of the system, and this is the Euler-Mascheroni constant. So here's an example of the comparison of this is a metastable state by comparing the average value of eta versus time. What you notice, this definition of Tm is when the system starts deviating, the alpha system deviates from the total lattice. And notice that as time evolves, we're going from 0.027 to 0.031, fairly small region, you have large jumps in when this occurs. This is a very sensitive measure of how quickly, at what point in time the system diverges. And you see you have a metastable state, and that's the actual equilibrium state. So it really takes quite a while to go on. And that's, that, okay. So, okay. I need to show the decay. The system does finally decay. The FPUT system, alpha, does go to equilibrium, but over a very, very long time scale. And this is, you see it's close to equilibrium until it's away from equilibrium, I'm sorry, until 10 to the 7th, and finally falls down and does go to the value you expect for this size system. Okay, this is, with only a couple minutes left, this is exactly how you approach equilibrium as a function of the value of the amount of nonlinearity. If epsilon is the energy density, this top figure shows you the black is instantaneous and the red is the average value. Let's look over here. These are the values of epsilon, the energy density. Blue is shown in the right. Blue is given by this. Magenta is 0.091. And you see it takes a much longer time. This is log t. This is 10 to the 10th out here for the magenta to reach equilibrium. But the original FPU value of epsilon is 4 times smaller than epsilon in this curve. And so it does reach equilibrium, but it takes much longer times than anyone has ever studied. So the simple answer and the take-home message of this slide is that the FPUT system has never been driven to equilibrium. This is our results. 1 minute, okay. Blue open squares are earlier work by Casati. The black dots are ours. And what you notice here is that there is the vertical line is where FPUT would be. Notice there's a break in slope here, and who knows whether there's another break in slope. So it's clear that it's going to be a very long time scale. With no time left, I think in terms of the lead to some questions, I will simply skip the rest of this. You can see it in the rest of the talk. And the speculations on the behavior in the real thermodynamic limit, n goes to infinity, energy density not equal 0. The simple truth is numeric can never resolve this limit because you can always demand longer times, larger n or smaller epsilon. The stickiness raises serious questions. I didn't go into it, but it's hard to resolve. And the best approach must be some sort of finite size scaling in n and epsilon. and that's currently what we're doing. And so, as we say in Shakespeare, the best lies beyond. So I'd like to thank you and the organizers and my colleagues who are shown here. Thank you very much. Question, yes.
Yeah, very interesting talk. I was wondering whether...
Excuse me, we need to use the microphones in order for the virtual participants to hear. Can someone, you can just try passing the microphones, but that'll work too.
I was wondering whether round-off error would become important when you run it this huge number of times, because you're always eventually going to run into round-off error in your computer.
This is extremely important, yes. The way we check it, it's a Hamiltonian system, and therefore it should be time reversible. And we do run the system out and verify that if we reverse the velocity, we can run back to zero. And we find these effects, that does eventually happen, that we because of chaos in the underlying system, we lose the accuracy. But the system, the things I've shown you are verified by going back to zero, and so the simulations are good. But no.
Can you comment on the stickiness that you didn't have time to talk about?
I think I'd better not. I'll talk about it later. But basically, what we show is there's a Q breather that comes in and lasts for a very long time in a region of phase space, and we don't quite know why. But it may be something like you see in low-dimensional dynamical systems where you have a contour that block the motion. So it's certainly something that's related to low-dimensional dynamical systems, but you're in a 64-dimensional phase space, so pretty hard to imagine how it goes exactly.
Thanks. It might be a naive question, but do you have a physical interpretation for why the relaxation of the metastable state to the equilibrium, to the thermodynamic equilibrium, is so slow? Is that something we can only really understand mathematically, or is there sort of like a...
Well, one explanation is that these solitons that exist do persist for a long time, and they lead to these recurrences. And the recurrences, the super recurrences, tend to make the system very stable. So that's basically the underlying thing.
With regard to the very long time to equilibration, I wonder if a reasonable strategy would be to introduce stochastic perturbations which would make the equilibration happen sooner, and then see in the limit of vanishing perturbation, if you can at least get trends, you might be able to extrapolate beyond the computable range.
That's an excellent suggestion. It's very much along the lines of what I said about trying to get a scaling between epsilon and n in our solutions. But that's true, and it's been useful in low-dimensional dynamical systems, say like the logistic map, to look at the different kinds of states you have by adding a stochastic perturbation. But you're absolutely right. That's a good idea.
I have a question.
Okay.
So I'm trying to get a physical sense of what determines the very long relaxation timescale. And of course, you mentioned at the beginning that if there are no nonlinear couplings, the infinity,
That's
trivially.
Right.
So is there some sense in which adding more nonlinear couplings reduces the time? Is there any quantitative way to put that?
Well, I mean, that's basically what we're studying. And you saw, I guess, in the one case, comparing it to the total lattice, which is integrable, so never reaches equilibrium, so satisfies your criterion there, that the time at which they started to diverge, FPUT and TOTA, jumped around a lot as a function of energy. Very, very sensitive. So there have been some speculations that this is due to wave turbulence, if people are familiar with that concept. Anybody know that?
I am, but
okay, yeah. But we've tried to find that. Lvov has worked on this a lot, and we tried to find that, but we don't get the resonances that he claims he finds. And so I talked to my big soliton friend Alan Newell, and Alan said, Lvov assumes you have a uniform state to start with, but we have solitons, not uniform state. So all those bets are off. So we don't know what it is, but it must be some sort of resonance phenomenon.
Interesting. Thank you. Are there any other questions? Sure.
Is it possible that there's some kind of a fractal system of equations? So you start with your original system of equations, and then you get an envelope an equation for the envelope of that's the soliton, but then that's a nonlinear equation, and so you can do an envelope for that, and that generates a new equation, and then you do an envelope for that, and you just keep on going, and you never get to the end?
That's a good question. I don't know the answer. I don't quite know how to implement that, but that's to me the main thing.
I have a question. Have you, there were some ideas or developments, like, trying to link work to, say, fractional derivatives?
This is exactly the same question, I think.
Yes.
Yeah, a fractional derivative. I mean, of course, famously, Kruskal worked on all that sort of stuff. I don't know, I'm not an expert in that, and I don't know what we would find, but if that proves to be productive, that would be great.
Well, there is no well-defined definition, final definition of fractional derivatives. So
Oh, yes, of course, but relating it to the FPUT equation is the question. We're violating all rules of timescale.
It's a short question.
Okay.
I missed your message on the difference between periodic and non-periodic boundary conditions on your results. So what's the really inference?
In the limit, of course, n goes to infinity, there shouldn't really be much difference, and there isn't. We can't go to infinity, of course, but we go up to 512. But the point of periodic boundary conditions allows the solitons to come back and continue. And so and the fact that Shastri and Young studied the total lattice with periodic boundary conditions was a strong motivation for us to use them as well. They've been studied before. FPUT did fixed boundary conditions mostly, but people after them used also periodic. And actually in these last papers, the last 4 papers, and they're some of them all have parts on periodic boundary conditions.
Okay. All right, the next speaker is